Okay, so we're looking at the 12th set of free response questions here. The first one gives me a table of selected temperatures of a teapot that is cooling from time 0 to time 10, and then we get some questions about it. The first one is an average rate of change at 3.5. So to do that, we're going to say that the average rate of change at 3.5 is approximately f of 5 minus f of 2 over 5 minus 2. F of 5 is 52. F of 2 is 60 over 5 minus 2 is negative 8 over 3, which can be listed as negative 2.666 degrees Celsius per minute is our average rate of change at 3.5. All right, so let's look at B. B gives us this expression, 1 over 10 is the integral from 0 to 10 of h of t dt. This is the average temperature in degrees Celsius of the teapot on the interval from time t equals 0 to time t equals 10 minutes. Okay, so then it wants us to calculate this using a trapezoidal rule. So 1 over 10 integral 0 to 10 h of t dt is going to be approximately 1/10 times, and in the first interval the endpoints are 66 and 60 with a width of 2. The second interval the endpoints are 60 with a width of 3, 60 and 52 with a width of 3. The third interval is 52 and 44 with a width of 4. The last interval is 44 and 43 with a width of 1. When you simplify this, you're going to get 1 over 10. That's going to be 126, 168, 192, and 43 and a half, which is 1 over 10 times 529.5, which is 52.95 degrees Celsius, is the average temperature in Celsius of the teapot from time 0 to time 10. It's an estimate using a trapezoidal rule, Riemann sum. Alright, so let's look at part C. Okay, so part C gives us the expression, the integral from 0 to 10 of h prime of t dt. It tells us to calculate this and then explain the answer. So this is the same as h of 10 minus h of 0, which is 43 minus 66, which is negative 23, which means the teapot cooled, sorry, spelling, there we go, cooled 23 degrees Celsius from time t equals 0 to time t equals 10 minutes. Alright, so in part D we get a cooling equation for a biscuit that starts at 100 degrees Celsius and then works its way down for 10 minutes. So the question is at the time t equals 10 minutes, how much cooler is the biscuit than the tea? Okay, so ultimately we've got to find the temperature of the biscuit at time 10, so the integral from 0 to 10 of b prime of t b prime of t dt is b of 10 minus b of 0, right? So if you rearrange this, you're going to get that b of 10 is 100 plus this integral. If you do that calculation in your calculator, you should end up with approximately 34.1827528. So what we need is the temperature of the tea minus the temperature of the biscuit at time t10. And if you take that, we know that h of 10 is 43. 43 minus this gives me approximately 8.817 degrees Celsius. So there's problem number 1. Let's move on to problem 2, right? Alright, so problem 2 gives us this drawing. Okay, so we've got this thing where this is e to the 2x, right? So this is from an interval from 0 to k, and they tell us that that point is k e to the 2k. Alright, so the first thing they want is the perimeter, right? We're also told that the value here is 1 because that's e to the 0, which is 1. Alright, so this length here is just going to be 1. This length here has to be k. This length here has to be e to the 2k, right? Because that's how tall that is. So what we're left with is needing like this part right here. Okay, so let's get these in there. You have 1 plus k plus e to the 2k plus something, right? So that we need a derivative for. So if y is e to the 2k, dy, or 2x rather, e to the 2x, dy dx is 2e to the 2x, which means, let's call this L. The length of that has to be the integral from 0 to k, square root 1 plus 2e to the 2x squared dx. That's the arc length formula. So the total perimeter will be the 1 plus k plus e to the 2k plus the integral from 0 to k of the square root of 1 plus 2 times e to the 2x squared dx. And that's the entire part A of the problem. Part B uses the same figure but asks for the volume of revolution, so let's do that. Alright, so again we have this, we've got this guy, this is 0, this is k, this is e to the 2k. So the volume of revolution is going to be v is pi times the integral from 0 to k of e to the 2x squared dx. So that's pi times the integral from 0 to k of e to the 4x dx, which gives me pi over 4 e to the 4x from 0 to k, which is pi over 4 e to the 4k minus 1. Because e to the 0 is 1, so that's my volume. Part C asks what is the change in volume with respect to time when the volume is, when k is 1/2 and dk dt is 1/3. So we just found that volume in terms of k is pi over 4 times e to the 4k minus 1, which means dv dt is going to be pi over 4. That's just a constant. Derivative of the inside, which is 4e to the 4k, right? And then that's going to be dk dt, because this is implicit. So dv dt is going to be pi over 4 times 4e, and the question is what happens when k is a half, so that's going to be 2. And then we get a third for dk dt, a third, not a sixth. The 4's cancel, so this is going to be pi over 3 times e squared. So that's all of part C. Let's move on to problem number 3. Okay, so problem number 3 is this graph that's out of 2 quarter circles and a line, and it gives us an integral function with a little added 2x in there. So this is pretty standard fare. Wants g of negative 3, which is going to be 2 times negative 3 plus the integral from 0 to negative 3 f of t dt, which is negative 6 minus the integral from negative 3 to 0 f of t dt. The region from negative 3 to 0 is the quarter circle radius 3 above the x-axis. So that's just going to be 9 pi over 4 quarter circle, not half circle. 9 pi over 4. And that gives us our value for g of negative 3. G prime of x is going to be, well, the derivative of 2x is 2. And by fundamental theorem of calculus, this is going to be plus f of x. So what is g prime of negative 3? That's going to be 2 plus f of negative 3. Negative 3, f of negative 3 is 0, so that's just 2. Alright, so that moves us on to part B. Part B is actually pretty straightforward. It asks us where is the absolute maximum. If you think about this, the absolute maximum has to occur when g prime of x is equal to 0. So this is when 2 plus f of x is equal to 0, which means we want to know when f of x is negative 2. The only place where that's the case is when x is 5 halves. You can get that from the graph. So if I look at this, on negative 4 to 5 halves, g prime of x has to be positive, so it's increasing. On 5 halves to negative 3, g prime of x has to be negative, so it's decreasing. So this means I have to have an absolute maximum at x is 5 halves. So there's A and B of the problem. Let's move on to C and D. Okay, so let's look at part C. We want all the values on the interval that have a point of inflection. We're going to have a point of inflection where the sign of the second derivative changes. The second derivative of g is just equal to the first derivative of f. On the interval from negative 3 to 0, f prime of x is bigger than 0. It's increasing. On 0 to 3, f prime of x is decreasing, or f is decreasing, so f prime of x is less than 0, which means that the second derivative has a sign change at 0. So g has a point of inflection at x equals 0. Alright, let's look at D. D, it wants to know what would be the average rate of change. The average rate of change here would be f of 3 minus f of negative 4 over 3 minus negative 4, which is -3 plus 1 over 7, which is -2/7. And it's pointed out that that's never equal to the, what do you call it, the instantaneous rate of change. So the question now becomes, well, why doesn't it have to be? Well, f is continuous, but one of the requirements of MVT requires f to be differentiable on the interval. We actually have 2 points of non-differentiability. F is non-differentiable at x equals -3 because I get an vertical tangent there, which means that the derivative is undefined, and at x equals 0 because I get a sharp turn, a cusp there, which means the derivative is also not defined. So MVT doesn't have to hold because it requires differentiability, which is why this is possible. Alright, so let's take a look at number 4. This is 2010 landfill containing 1,400 tons of solid waste. There's a differential equation for how the waste is going to accumulate over the next 20 years. So the first thing is like you find the line tangent at time 0, so we're going to linearly approximate this. We know that W of 0 is 1,400 because that's a data point. The derivative at time t equals 0 is going to be 1/25 times 1,400 minus 300, because W when t is 0 is 1,400. So this is 1,100 over 25, which is 44. So W minus 1,400 should be 44 times x minus 0, which means W at time t is 44x plus 1,400 is my linear approximation. T. No x's. T's. Alright, so it says use this for a quarter of a year from now, so we want to do W at 1/4, which is 44 times a fourth plus 1,400, which would be 11 plus 1,400, which is 1,411 tons. Alright, so that one's pretty straightforward. 2 things you need to have there. You need to have the linear approximation and the actual approximation at time t equals 1/4. Let's do part B. Okay, so part B of the problem says that we want the second derivative, which is kind of expected. If dw dt is 1/5 w minus 300, so d2w dt squared is going to be, that's 25th, 1/25 times dw dt, which is 1/106/25 times w minus 300. Okay, so at t equals 0, this is going to be 1/6/25, 1,400 minus 300, which is 1,100 over 625, which is greater than 0, which means that I am decreasing and concave, sorry, not decreasing, I am increasing here, and concave up. Alright, so if I think about this, here's my point at time t equals 0. If I am increasing and concave up, right, and I make a linear approximation here, the linear approximation has to be an underestimate. I forewarn you, I put decreasing on the answer sheet. I'm going to fix that right now and hopefully repost if I can remember to do that. That is actually increasing. The amount in the landfill is increasing. All right, so there you go. Let's look at part C of this problem, which asks us to solve the differential equation. All right, so the differential equation here for part C, dw dt is equal to 1 over 25 times w minus 300, which means that dw over w minus 300 is equal to 1 dt over 25. Take the antiderivative of both sides. We get the natural log of the absolute value of w minus 300 is equal to t over 25 plus some constant. We have an initial value where w is 1400 when t is 0, so this is going to be the natural log of 1100 is c. So the natural log, and we can just make this, because we're on 0 to 20, which is going to keep this in bounds, t over 25 plus the natural log of 1100. Take e of both sides, we get w minus 300 is 1100 e to the t over 25, which means that w of t is 1100 e t over 25 plus 300. And there you go. So that's the solution to the differential equation. Let's move on to number 5. Alright, number 5 is Taylor series stuff, but it's all known Taylor series business. So 5 part A asks for the first 4 terms of sine. So sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. You should have that committed to memory. Sine of x squared just says plop that in. X squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 7th over 7 factorial. Alright. Part B says play the game with cosine. Cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And then we want the whole equation. So that's sine of x squared plus cosine x. Alright, what's the first 4 non-zero terms? Well, the constant term has to be one of them. We have no x term, so x squared is going to be x squared minus x squared over 2. So that's just going to be x squared over 2. I only have 1x to the 4th term here, so we can put that in there. And then I've got this situation where I have like minus x to the 6th over 3 factorial minus x to the 6th over 6 factorial. So thinking a bit here, this needs a common denominator, which is going to be 6 factorial. So I need 4 times 5 times 6 up here. And then now I've got the common denominator, right? Alright, so this stays the same. 4 times 5 times 6 is 120. And then I get one more, so this is minus 121 x to the 6th over 6 factorial. So that's part B. I'm actually going to do part C right here, because this is actually pretty simple. This has to be the sixth derivative of x over 6 factorial has to be negative 121 over 6 factorial, which means that the sixth derivative at 0 has to be negative 121. And that's the whole problem. All right, so there's the problem set for number 12. I hope this is helpful. Again, do the drop-ins as you need to, and we'll go on from there. Thank you, and have a great day.